Section 1.3 is on page 15, talks about directed fields. The same directed fields, you call them slope fields back in 1150. Consider dy dx equals some function of x and y. So remember, this is a derivative. And if you recall, wherever the derivative is positive, the function is increasing. Wherever the derivative is negative, the function is decreasing. Wherever the derivative equals 0, that's called a critical point, right? That's when you have nor increasing nor decreasing. That happens at like a possible maximum or minimum, if you recall. So the short graphs, short lines like these lines right here, resemble the slope field. And this is what we're doing. We're trying to find a solution. We're graphing the solution to this differential equation by simply using our knowledge of first derivative test. So if I look at problem number 2, this would be on page 21. It says the directed field for dy dx equal 2x plus y is shown in this figure. They gave us the graph already, and it's right there. A. Sketch the solution curve that passes through the points 0, -1, -2. If you were to start right there, so think of this. Think you're running water left to right, and those levels you could turn any way you want. If I was to release a floating ball on top of the water, and this is how these are pushed left to right, of course. The water is being pushed always this way. If it's going to run straight, if you release a ball right there, how would it travel? I'd say it's going to travel in a path, something, it doesn't have to be exact. So you could say it's going to come down, and then it's going to turn there and run up and all the way up. And from the left, if you notice from the left, the path, it looks like something like this. That's the solution. We could find the solution, and we will do that in the next lecture today. You'll find all of these solutions. What if so this is part A, that's all I want. All what they said, list the solution we did. In part B, sketch the solution if you are looking at -1, 1, 2, 3. What if you released the floating ball right there? Don't you think this is going to come up? Something like this. And from the left, you want to make it a smooth curve. So you could say, well, it might have came from this. And what do you think the limit is as x approaches infinity for B? Well, as x approaches infinity, right, of dy dx, wouldn't that be infinity? And how about the limit as x approaches -infinity? What if you want the other bound? Isn't that approaching infinity as well? And that's pretty much it. Number 4, we're going to graph this. They say, this is problem number 3. You're going to do number 3 for homework. If this force is nonlinear, a possible model would be, yours is 1 minus v over 8. We're doing 1 minus v cubed over 8, modified slightly. Redraw the field from 1.14. They give you the field in number 3. Let's just do it ourselves. Incorporate this v cubed independent. Sketch the solution with initial values if you're looking at 0, 1, 2, and 3. And you notice this right here is t. And we're trying to graph v of t. The key element that we didn't talk about in 1150 is actually setting that equal to 0. That would mean that 1 equal v cubed over 8, meaning if you cross multiply, and v would be cube root of 8, which is up to. So this is what we know. We know the derivative equals 0 at 2. At 2, this is when this is equilibrium, right? As long as you walk on that line, you're not being pressured up or down. Now let's see what happens if we pick a point below. If I was to pick a point below 2, let's say v equal 1, and I put that in there. If I let v equal 1, what would happen? 1 minus 1/8, isn't that positive? Positive 7/8, so remember, that's a slope of 1, that's a slope of 2, and that's a slope of a half. So 1 minus 1/8, that's 7/8, very close to that, something like this. How about if I went to v equals 0? What if I went to 0? If I put a 0 there, wouldn't you say that's 1? What if I went to negative 2? What if I went to negative 1? If I put a negative 1 there, wouldn't that be plus 1 plus 1/8, a bit bigger? Well, that pretty much gives me a feel of what happens if you are beneath this. What if you're above? What if you went to v equal 3? If you put a 3 there, I'm sorry, 1, 2, yeah, if you put a 3 there, wouldn't that be 1 minus 27/8? Isn't that negative? And if you go to 4, you're going to notice it's a steeper. So do you see what's happening here? If you are beneath, you're being sucked up to this. And if you are above, you're being sucked down. Now, all what they want us to really label few of these. They say, sketch the solution with initial condition if v of 0 equals 0. If v of 0 equals 0, if you start right there, then what's going to happen? Isn't this going to level off and run right there? You could say it's going to come this way. That's fine. If you run v sub 0 equal 1, what if you start right there? Well, the same deal. And what if you went to 2? If you are at 2, you're leveled off. You're not going up or down. And what if you are to run to... Did I use that color? What if I was to go to 3? If I am at 3, do we agree that that's kind of how the graph look like? What is the terminal velocity? Terminal velocity happens when you let the system run for a very long time. What would happen to this? This will level off next to 2 no matter where you start. It turns out that's the terminal velocity. Alright. Next problem is number 5. This is also on page 21. I'll give you a page, yes. So I'm going to do 5 and I was going to do 6, but 6 is nothing like this. Again, it says the logistic equation for population in thousands of certain species given. Well, if it's population, then we only talk about positive population. There's no negative population. You're really looking just at quadrant 1. It says the PP is the population is changing with respect to time. So this is T, and this is the change in population. If I set that equal to 0, doesn't that say P into 3 minus 2P equal to 0? P equals 0 or P equal 3 halves. If I mark those two lines, 3 halves is about 1.5. It's right there, right? Right? So there it is. I'm sorry. I keep on saying this is popular. I'm graphing the solution to this. I did that up there, right? Yeah, that's the velocity, yeah. The change of velocity is acceleration. So here we go. Now, I do realize doesn't make sense to pick negatives, but if I was to pick a point between 0 and, well, let's say 1, if I was to pick p equal 1, do you see that will be 3 minus 1? So dp dt, which is the change of p with respect to time, would be 1. So there, it's going up. I could pick a half, but unpleasant. If I pick 1/2, I'll notice that 3/2, that will be times 3 times 1/2. That will be 3/2 minus a half in there minus 1/2. That will be 2/2, which is 1. Wait, that can't be right. If I picked 1, if I put 1 in there, 3 minus 2. Okay, if I put 1/2, that's 3/2 minus minus 2 times 1/4, which is 1/2. That will be 2 over 2, that's also 1. So there. No need to pick negatives, that doesn't make sense. If I go above, what if I picked 2? P equal 2. 6 minus 4 times 2, that's negative 2. So a bit sharper than the mid, I should say. I made this to be negative 1. I want it to be a bit more sharp, so there. And how about if I picked, let's say, p equal 2, 3. You know what I mean, 3. That will be 9 minus 12, which is negative 3. It's even steeper. So what does that mean? Let's see what they are asking. A, sketch the directed field by either a computer software or the method, okay, whatever that is, we just sketched it. B, if the initial population is 3,000, that is P of 0 equal 3. P of 0 equal 1, 2, 3, right there. What can you say about the limiting population? So in part B, what is the limit as t approaches infinity of P of t? What do you think is going to happen? Isn't that going to be 3/2? In part C, P of 0 equals 0.8. 0.8 is about right there. What do you think is going to happen in part C? What is the limit as t approaches infinity of P of t? What do you think that is? Well, isn't that going to level off next to that equilibrium? That's also 3/2. So it's asking a simple question. Can the population of 2,000 ever decline to 800? Population of 2,000, let's see, where's 2,000? P of 0 equal 2, that's right there. That could decline to at most as 3/2. So the answer is no, it can't. The last problem up, I want to tackle number 12. It says draw the isocline with their directed markers and sketch several solution curves, including the curve satisfying the initial condition. Alright, so dy dx, this is x, this is y is the solution. Set this equal to 0, y equals 0 is the equilibrium, right? That's like the critical value. If I pick a point above, y equal 1, if I pick y equal 1, do you notice what happens? At y equal 1, then the slope would be 1, and that runs for any value of x. Yes, I am picking the simpler cases because they're more complex. Turn out to be just a bit more work, but it's the same idea. How about if I went to 2? Slope of 2, it's sharp, more sharp than 1. And obviously if I pick 3, I'm going to get 3. That thing is shooting up a lot faster. Now what if I picked negative 1? What if I picked y to equal negative 1? Slope equaling negative 1 will look like this. That's the slope of the tangent to the curves. And how about if I picked negative 2? A negative 2 is steeper. It seems if I pick values left to right, that's how the solutions look like. This is repelling everything sort of exponentially. If you are above, that's if the initial case condition is above the x-axis. And if it's below the x-axis, it seems it's repelling in a negative exponential function. So what happens if you happen to be at the point 0, 1? You will follow this path, this form of an exponential function. Again, we could do the more complex, just takes more work, but this is the gist of the idea. And we come back to this idea, I think, later on. Maybe, we'll see.